It's common for people to want to talk about ANOVA in these kinds of workshops. I'll take this opportunity to remind you that ANOVA is just a term for a particular way of representing the results of regression models in most cases. But I'll show you some functions related to this kind of representation. First, I want to remind you about the table function. So I'm going to do like a model that has score as the response variable and race as the predictor variable in this case. So let's tabulate race and remind ourselves what the data set looks like. So remember, this is a small data set, so I could print the whole data frame to the console, but normally I wouldn't do that because data frames are generally big when they're actually like data we want to work with. But it had a column called race, and it has these three values, Asian, black, and white, in it. So when I call table of race, then I get a table that tells me there's 6 cases with the value Asian, 6 with the value black, and 8 with the value white in this data set. I had to do data1 $ race because that tells R where to look for this race variable in the data1 data frame. Remember, race is just a column, a vector that's in this data frame, which is a table or a list of column vectors. And I can do the same thing to say get a histogram of score. So here's that overall histogram of score. Helpful to remind myself that it ranges approximately from 0 to 10, and maybe not much else. So let's fit that model first. I will first just store the result of a regression model in a new name that I'm calling model.2. Above I used model.1 for something else, so I'll call this one model.2. You might want more descriptive names in real life, but this is where we are right now. And this is just a regression model of score based on race with data1 as the data set. And I can look at summary of model.2 to see the regression table. And I can also call summary.aov of model 2. So summary gives you the default summary. Summary.aov gives you a different kind of summary of that regression model that puts the results in a table more like a traditional ANOVA table. So here we have a row for the effect of race, effect used loosely. There's no reason to think that this would be causal if this was a real data set, of course. It has 2 degrees of freedom because there's 3 unique values, and the F-test indicates that this factor is not significantly related to the outcome of interest here, the score, which we already kind of knew because both black and white were not very different, not significantly different, and not very different from the Asian group in this data set. I can also jump straight to, instead of summary.aov, this ANOVA function, which is the one I use most often for some certain other purposes that I'll discuss in a second. And it's in this case, a similar function, but ANOVA can be used to compare models in a more convenient way. In this case, it gives a very similar table. I can also use the built-in AOV function to fit a model directly. So here I'm calling this model 3, and that's the result of the AOV function, which is like the LM function, but it attempts to do ANOVA in the first place. And I have the same formula specification and the same data argument. And if I look at a summary of that, it gives me this same ANOVA table. Even though I'm just calling regular summary because this object is already, R is thinking of it as an ANOVA object. People will want to know about factorial ANOVA, and you can do that. You can do that using regression models, and I encourage you to do so. Here I've done summary of AOV, of score, modeled on the basis of race and gender and their interaction. And I get this kind of a table, which looks more like a traditional ANOVA table. But careful not to interpret these lower order terms as traditional main effects. I'll explain a little bit more about that in a second, but this table is at least useful if you want for getting information about the race by gender interaction which you would reasonably conclude is not statistically significant. Unlike in SPSS, you can easily leave out the interaction term and still get this kind of ANOVA style output. So I can do the same thing, but with the plus sign instead of the asterisk. And then I get an ANOVA style table that just has these two terms instead of the interaction term. But again, these terms are maybe not what you would expect from a typical main effect. So we're going to talk about that in a second, but you can always just fit a regression model using LM with the variables that you want if you want to really understand what's going on, and I encourage you to do so. But first I want to show you one of the reasons why I would do this. Well, I guess I kind of already did, but I'm going to show you again one of the reasons why I would do this to emphasize. If I look at the summary of the linear model, of the formula score tilde race asterisk age. I'm looking for the race age interaction, and R, as we've already learned, will give me all 5 terms necessary to estimate that interaction automatically. There's 5 terms because age has 1 degree of freedom, but race has 2. And so the lower order effect of race has 2 terms associated with it. Here, and the age has 1 term, and then the interaction is represented by 2 separate terms for a total of 5 terms. And if I want to know if the overall race by age interaction is statistically significant, which is a question that comes up in lots of psychology applications, then this doesn't, I mean, it makes this output here makes the answer to that question fairly obvious, but it doesn't provide a formal test of the overall race by age interaction that you might sometimes want. For that, you want to compare a model that has just these 3 terms to a model that has all 5 terms. And one way you can do that is fit both of those regression models and compare them using ANOVA, the ANOVA function. So I'm going to show you that quickly first because I think that's useful to know about. So here's one, and here's the other, right? This model has all 5 terms in it. This model has just those 3, and I can compare them using ANOVA. What I've done here is I've just, I'm calling the function ANOVA, and I'm supplying to it, I'm going to put spaces in to be clear about what I'm doing, 2 arguments. The first argument is a model that has the interaction, and the second argument is a model that does not. I've split it across multiple rows so that you can see it all on the screen, but that doesn't matter. I'm going to run it, and it will give me a comparison. I probably should have put the plus sign first, but it doesn't really matter. The comparison between these 2 models has an f-test that's not statistically significant. So this is one way of ascertaining that the race by age interaction is overall not statistically significant. But you can also jump straight to summary.aov of this regression model, and the 3rd row provides a test of this f-test with 2 numerator degrees of freedom. That's the same f-test obtained by comparing the models explicitly right here. So it's a shortcut to get that kind of overall test of an interaction effect. But here's where I talk for a second. I'm just going to talk, there's not code representing this, about what people are used to in talking about ANOVA versus what you get using some of these functions in R by default. If you're an SPSS user, you're probably accustomed to running a function called ANOVA or unit ANOVA, and seeing a table that represents a full factorial design with main effects and interactions that can be sensibly interpreted right off the bat. And none of the functions that I've described above give you that kind of a traditional ANOVA table for a full factorial design. And there's a reason for that. ANOVA can be thought of as a particular strategy for summarizing the results of 1 or more regression models. And when your most complex model includes a 2-way interaction, then you are expecting there to be 2 main effects as well, but there's no single definitive way to summarize those 2 main effects. That's a decision to be made. The same goes for the two-way interactions in the presence of a three-way interaction and so forth. You have to decide how to describe those lower order effects. And the options that you have for how to describe those are often referred to as types of sums of squares. Type 1, type 2, type 3, and so forth. If you have a simple 2 by 2 design, then type 1 sums of squares would test the terms sequentially, so that the first main effect is tested on its own, not adjusting for the second main effect. The second main effect is tested adjusting for the first. And then the interaction is tested adjusting for both main effects, as it should be. I recommend not using that approach with type 1 sums of squares because most psychologists will find it counterintuitive to test one main effect adjusting for the other, but to test the other main effect not adjusting for the other one, if that makes sense. Unfortunately, that is the default behavior of the built-in AOV function in R, and there's reasons for that. It makes it more consistent with the LM function. But that's why I said careful not to interpret the lower order terms when I introduced that function a second ago, right here. Type 2 sums of squares is a more sensible option in my opinion. That tests the main effects both adjusting for each other. In other words, that approach, the type 2 approach, would be similar to fitting one regression model with only main effects and another model that has the main effects and the interaction term. And that, to me, is the easiest approach to understand and the one that I prefer. And it also happens to be the default for the capital A ANOVA function in the car package. I haven't loaded the car package right now, but I'm typing it at the console just so you can see what I mean. It's capital A and then lowercase ANOVA, and that function is present in the package called car, which I will tell you a little more about later. And then type 3 sums of squares would test all of the terms in the same regression model, meaning that the lower order terms would be simple effects instead of overall main effects. Most implementations of type 3 sums of squares automatically code your variables, for example, by contrast coding or centering them, in order to estimate those simple effects at useful points, such as the average of the two conditions or the weighted average by the sample sizes in the two conditions in your 2 by 2 design. And that's the default in SPSS. This is my long-winded way of explaining what the default in SPSS is for those of you who are accustomed to using that. SPSS gives you type 3 sums of squares with contrast coding by default. But that's a decision that SPSS kind of hides. And that's something you'll notice with R. In general, you are going to understand what's going on more once you get used to it. But sometimes you are forced to make decisions that previously were kind of made for you if you're switching over from a piece of software like SPSS. I realize this is a long explanation. I'm just sort of pausing the main portion of the workshop to do it because in past iterations of this workshop, I found that people leave this little ANOVA subsection somewhat confused. You're welcome to reach out to me with questions, even if you haven't thought of those questions right now. I'm happy to talk about it. If it all seems sort of confusing, you always have the option of just specifying the exact regression models you want to use using the LM function and not bothering with any of these AOV or ANOVA functions.